Okay, so for this problem, we have a circuit under DC conditions, and we're supposed to find the current through the inductor. Well, under DC conditions, after some time has passed, so DC, we've got a direct current, it's not changing, and you've had time to reach steady state, then a capacitor acts as an open circuit and an inductor acts as a short circuit. So when a current first starts to flow, the inductor opposes the current, so it acts to kind of push the current back. But after enough time, then and it acts because as the current is just starting, it's changing, and that induces a magnetic field, and the magnetic field opposes the change that's coming from the increase in the current, so it opposes that. But after enough time, the current is no longer changing, so the current's not changing, so there is no magnetic field, so there's nothing to oppose the current. So after enough time, the flow through an inductor acts as a short circuit. A capacitor, the symbol for a capacitor are these two lines, and that's because mini capacitors are parallel plates. So you have a parallel plate capacitor. It looks like this, so it would be, two plates parallel to each other. And after enough time, when the capacitor is fully charged, then those plates, it is a break in the circuit. So when the capacitor is not charging anymore, the current can't flow between the two, and so it acts as an open circuit. So what I like to do when I am drawing these things under DC conditions is I like to redraw them with the capacitor and the inductor as open circuits and short circuits. So we're not using the switch in this one. We're assuming it has been closed for a long time, so there's a switch right there. And if the switch has been closed for a long time, then this inductor now acts like a short circuit. So I just draw it like that, and I put the little dots there to remind me that's where it is, but it just acts like a straight wire. And I'm looking for the current through that inductor. This is 15 kilo ohms. This is 15 kilo ohms. And this is also 15 kilo ohms. And a 9 volt voltage source. So this 15 kilo ohm resistor right here, and the 15 kilo ohm resistor on the top, these two are in parallel. They're in parallel because this side is all at one voltage. It's all connected by a conductor. And the other side is also at the same voltage, whatever that is. And so they are in parallel. And if I have two resistors in parallel and they're identical, then the equivalent resistance is half of the is half of the original resistance. Okay, so I need to find the current through this right-hand branch here. I'm going to do some simplification, but I need to remember that I'll have to come back and unsimplify it because I'm changing the exact branch that I want to find the current through. Oh no, I decided I wanted to do this one by mesh because your homework asked for mesh. So I'm not doing resistor simplification. I'll do a mesh analysis. And I'll call this first mesh I1 and the second mesh I2. And now if I look for my mesh equation for I1, I'm coming into the negative terminal of the 9-volt voltage source, that's minus 9, plus I1 times 15 kiloohms. And then that middle branch is plus 15 kiloohms times I1 minus I2, and that equals 0. And the second mesh, coming up through that middle branch, that's 15 kiloohms times I2 minus I1, plus, and then going through that top resistor, 15k I2, equals 0. And now if I simplify these, this top equation becomes 30k I1 minus 15k I2 equals 9. And the bottom equation becomes negative 15k I1 plus 30k I2 equals 0. I can multiply the bottom equation through by 2, get negative 30k I1 plus 60k I2 equals 0. Then I can add the top equation and the bottom equation together. And those cancel, and I get 45k I2 equals 9. I2 equals 9 divided by 45,000. Or I2 equals 0.0002 amps, which is the same, so 0.0002 amps is the same as 0.2 milliamps. Now I solved for I2, and that turns out to be the I that I wanted because that is the current through the inductor.